intermediate glucose oxidase is not very different in cost. Now, on the triglyceride determination, the point of care device, the first series, Mark 1, named after my significant other, is going to attack the issue of glucose accuracy. That's what is required. If I may ask you, Professor Malhotra, what is the accuracy in the glucometer that you showed me?
Around 15%, 10 to 15%.
That's the real problem there. The second step is going to involve cholesterol and triglyceride. HbA1c is fairly constant. It's enough if you check it every 4 months or 5 months. And that seems to be a better marker. In order to evaluate the risk, we need a totally new composite index. We are working on it. My problem, I am caught between applied mathematicians, engineers, medical scientists, physiologists, protein engineering people, electrochemists, photochemists. I hate to say when I come to India also by the tantrics. There's a whole array of people I have to deal with on. And therefore, at the end of the day, I feel that I'm not a specialist in any one of them. That also is a big problem there. So if you put me in one institution and say, this is your place, likely I will wander from there. So you need some floating population like me, who are attached to an institution, but they are all over the place. And who conducts a class across the globe, which is not liked by, I'm sure the Vice Chancellor will not like the idea of classes being conducted by Skype.
You have to be Krishna.
Now, on the HbA1c determination, the first step is deglycosylation, second is proteolysis, and then the treatment with fructosyl-valine amino oxidase. That protein has been around for 20 years, but took a lot of effort to clone it, expose it, mutate it. Commercially it's available, of course. All the commercial samples, you've got to be very careful. Impurities can be there. The best of experiments, an impure protein is as useless as worst experimental methods being applied on a pure protein. So you've got to be very careful. Till this day, I have not received a single cloned, expressed, recombinant protein from any laboratory in India. The only thing we ever got from Balaram was on peptides. It has been somewhat mind-boggling. We have Surolia sitting here who will challenge it. And we got, Virendra up in the next door. We got several other groups. We got the Center for Cellular Molecular Biology, Indian Institute of Science. And there are several places they can do it. But for some reason, I have not been able to get a single protein engineered, expressed, overexpressed, and purified and mutated here. Now, what is the story across the Himalayas? It's working very well. It is working very well with, of course, they are more disciplined. I think we have too much of democracy and they have less democracy, and that seems to be probably the answer too. Now, fructosyl-valine amino oxidase also has a fat cofactor. So these are the steps involved. Now, how does it work? Fructosyl amino oxidase catalyzes the oxidation of the CN bond, linking the C1 at the fructosyl moiety and the nitrogen at the amino group of fructosyl amino acids. The reaction proceeds to an unstable shift-base intermediate, which hydrolyzes to produce glucosome and an amino acid. The enzyme reduced fat cofactor is then reoxidized by molecular oxygen with the release of hydrogen peroxide, which can be detected electrochemically. That's the New England Journal of Medicine paper, not necessarily on the engineering aspects and the fundamental medical aspects of it. New England Journal of Medicine grew out of Harvard Med School, and we also have a similar invitation from Lancet. So it's kind of this 2012 and 13, 14, I think it's going. My style of management is different. It's more decentralized. I noticed there is too much a centralized administration in India. That is also another reason why progress may be slow. Now, expression of the the glucose oxidase, cholesterol oxidase, esterase, lipase, and fructosyl amino oxidase is done in the yeast system. We have a Chinese molecular biologist who is a specialist in Pichia pastoris, and we cannot do it in E. coli, so we go to the yeast system. Now, so that has been perfected. That's the one that will be used commercially to produce large amounts as well. So the future factories will not be steel plants perhaps. It's going to be protein based, steam belching, huge factories, cumbersome, clumsy, would probably be a relic of the last century as we advance towards the later part of this century. There are several steps involved: transform into the Pastori strain, plate transformers and medium containing zeosin or blastocidin, select the colonies for small scale expression, choose the clones to the highest expression levels for large scale expression. There is a control methanol and glycerol feeding rate. Finally, we have to purify it extensively. Now, at the heart of all of this, whether it is a solar cell or a fuel cell or a sensor, we have a bio-nano interface. There's an interesting paper in Materials Today, impact factor is 12.8, the last August, where we discuss the interface called the bio-nano interface. Bio-nano interface is the gateway through which the electrons flow. It could be organic, inorganic, or inorganic bio, or a metal oxide, organic metal oxide. Those things become very important in the inorganic, inorganic bio, in fuel cell and solar. In solar cell, it could be organic, or even a polymer organic. So all permutations are possible. So, how do we maximize this electron flow without losing it? How do we channel it from one side to the other side? Is a major bottleneck in sensors. Platforms for anchoring proteins, protein carbon nanotube electrode, immobilizing the protein. Three-dimensional electrode, forget it for the moment, improves sensitivity. The figure shown here is an obsolete paper now. Some papers have to be decommissioned, I think. There must be some way which we decommission papers and people will not even quote them in the curriculum today, making it much smaller. For example, this paper is a beautiful example of that. It's a 2 nanosecond molecular dynamic simulation. Today, we are fighting with the reviewers at 200 nanoseconds. We are talking of milliseconds dynamics. Here is another area where India needs to do tremendously. All attempts to link up, I have never seen a param in my life. If param is a beautiful bride, I would like the bride to be shown so that people can look at it and say param is a teraflop machine. There are teraflop machines. It is not commercially, I don't know how many institutions have it. India must make a great effort in linking up all these computers. We are now using the Pittsburgh teraflop supercomputers. Now that should stop. Large-scale molecular dynamics, large-scale density functional theory, astrophysical calculations, Mars probe, even I'm sorry to say, simulation of a thermonuclear weapon. That's how I think some of these things started with the embargo from the US. Whenever you are faced with a challenge, a crisis, you work better. In fact, I've done far more work under conditions which were not the most optimal. That doesn't mean starvation, but I think the creativity and opulence don't seem to go together at all. Now, here is a 100 nanosecond snapshot from molecular dynamic simulation of glucose oxidase interaction with graphene. The entire calculation took several months in the Pittsburgh teraflop supercomputer. A Polish group, we have a very productive engagement with Poland. Except don't ask me to pronounce their names. There are tons and tons of Polish people in our papers, in Warsaw, in Lublin, in Krakow, in Warsaw, all over the place, in Gdansk. And that paper is in PNAS, and it's 100 nanoseconds, and we had great difficulty in convincing the reviewer 100 nanoseconds is okay. So where does 2 nanoseconds go? It is not. I seriously consider small, thinner CVs, not long ones. Just quote the papers you have in the last 3 years. Even the impact factors could be misleading. It is not necessarily a reflection of the work.